The second part of this problem says that we want to prove that the series converges. So if the series is converging, we're talking about an infinite sum, or S. So the series converges to R over 1 minus R all squared. And this is for R is less than 1, so this is relating to the infinite geometric series. Okay, so firstly, I want you to make sure that you know that the infinite geometric series formula is when we have I is equal to 0 to infinity of R to the power I, as long as R is between -1 and 1, so that's what we have here. It will converge and it will be an infinite geometric series which has the formula 1 over 1 minus R. Okay, so we're going to define this, and it's important to notice that it starts from I equals 0. If it's not I equals 0, we kind of have to adjust for that. Okay, so that's one thing. So the other thing is trying to prove that the series converges. So we're trying to calculate an infinite sum, and we're trying to show that, and we're going to start with what we just proved here. Sn minus Rsn is equal to this expression on the right-hand side. So we're trying to find an infinite sum, so we're trying to find S. So what we're going to do first is we're going to factor out that S, and we're going to end up with Sn 1 minus R. Now we're going to take a limit on this because we need to find S infinity. The other thing is this I equals 1 to n R to the power I looks almost exactly the same as our infinite geometric series, except we start at 0. So we're going to match this up. So we're going to make this the same from R equals R to the power I. We're going to start it at 0 instead of 1. So that means that this term that we're looking at has an extra times R. And how I'm going to account for that is I'm going to take that R out on the outside of that. R times, now I can start at 0 to n, R to the power I. Now I'm doing that because now that it's starting at 0, this is the same as our infinite geometric series, and I have an expression of 1 over 1 minus R that I can replace there. And notice that we're counting for the number of terms in the notation. So we're changing the number of terms. We had to kind of adjust the expression for starting at 0 instead of 1. This is more of a problem from our starting point than our ending point. So the rest of it is 1 or minus n r times r to the n plus 1. Okay, so we're trying to find the s value, so we're trying to find a limit. So I'm going to take a limit of this expression. So I'm going to take the limit as n approaches infinity of Sn. Okay, and that's what we're trying to prove that the series converges for that. Now I'm going to take the 1 minus r and divide it on the other side, so 1 minus r. And then the rest of the expression is going to look like this. I'm going to replace that red series with the function 1 over 1 minus r, because at infinity, that is going to be the same thing. And we're going to take the limit also of this expression here, n r to the power n plus 1. Now that n r to the power n plus 1, if we take a limit of this, since r is less than 0, or sorry, r is less than 1, that's going to become 0 as we let n go to infinity. So if the base is less than 1, some number less than 1 to power infinity is going to be equal to 0. So that's going to be 0 when I apply my limit. So then my equation is going to look like this. I take the limit. I'm going to get the sum s, the infinite limit. Sorry, the infinite sum. That's going to be equal to going to be r over 1 minus r minus that the limit of that's going to be 0 over 1 minus r. Simplifying this expression, I end up with s is equal to r over, and the 1 minus r's can come together in the denominator, so 1 minus r all squared. So my infinite sum is convergent, and it's equal to that expression. And I've done that I showed that using a limit and replacing the sigma notation part of the original expression here. I rearranged it a little bit so I can use my 1 over 1 minus r, which is equivalent to that infinite sum.